Good morning, class. Homework yesterday was number 921. Morning, Sibuit. Hi, Timmy. Morning, Freeman. Okay, we have 4 people online. Sufficiently straight, I think. Hi, Audrey. So, number 921A. Oh, INI. Right. PF3. April the 2nd today. So, as with all diagrams, as with all diagrams, we have to first start off with the Lewis structure. So, we'll draw a T-chart and see how many valence electrons we have. We have 5 in phosphorus, 7 in fluorine times 3 gives you 21 plus 5, or 26 electrons to account for in phosphorus trifluoride. So we'll draw the Lewis structure first. Disperse the valence electrons. So that's using up 3 times 6, 18, 20, 22, 24, 26. So the last 2 go on the central atom. And that gives us 4 domains. So 1, 2, 3, 4 domains, of which 3 are bonding pairs. 1 is lone pair. If you look at your chart, that means it's pyramidal geometry. So we're going to draw it like this. I like to draw the lone pair pointing straight up. Make a little cloud, looks like a ghost. And then 1 in the same plane of the board. 1 coming out at you, and the 1 going behind. Okay, so the molecule looks like a tripod. And the bond angle you can predict is going to be around 107. This molecule is definitely polar because the fluorine atoms are much more electronegative than phosphorus, so they all have dipoles going this direction. So the resultant dipole would be like that, pointing downward. So the molecule is polar. It's not a symmetrical molecule, so the dipole moments do not cancel in this case. Then you have a methane. It's not methane actually. It's a what's it called? Carbocation. A methane carbocation. So if you take a proton off a methane molecule, you get a carbocation. So methane with a positive charge. Let's see what kind of geometry our carbocation would have according to Vesper theory. It's B. Take the account of the number of valence electrons. You got carbon, you got hydrogen. There's always 4 electrons associated with carbon, 1 with each hydrogen times 3, and it's missing 1 electron, so you're going to subtract 1. So you're just going to be minus 1. So really you have to account for 6 electrons in this molecule. You're going to get 3 domains, and obviously the carbon does not have a satisfied octet. This is not a stable species. It can persist if it has no other choice. For example, if you're conducting a reaction in a vacuum, a molecule like that could persist if it has nothing else to bump into, because it's not a very stable configuration for carbon. They're all bonding pairs. So this is going to be a trigonal planar, according to Vesper theory. So you're going to have a 120-degree bond angle there. It's going to be sp2 hybridized. Next you have BRF3. Bromine trifluoride. No formal charge on there, right? So you got bromine and you got fluorine. Bromine has 7 valence electrons. So does fluorine, and there are 3 fluorines. So you got 28 valence electrons to account for. The air is so dry in Edmonton that this board is drying from behind. It's starting to bow, bulging outward, and you see it's developing little bumps on it. You can feel them. You can feel them on the edges. I doubt you could see them on camera, but I can feel them. So you have bromine at the center. Disperse the valence electrons on the fluorines. And that's going to use up 6 times 3, 18, 20, 22, 24, 26, 28. And the way you've drawn it here, will there be any formal charges? Let's see, 2, 4, 5, 6, 7. No, because bromine wants 7 and it has 7. So no formal charges. That is the correct Lewis structure. It has 5 domains. 1, 2, 3, 4, 5. 5 domains. 3 bonding and 2 lone pairs. That 5 domains points to trigonal bipyramidal geometry, but because you have 2 lone pairs, those lone pairs are going to try to get as far apart as possible. So what they're going to do is they're going to end up equatorial, so they can maintain a 120-degree angle with each other and a 90-degree angle with the bonding pairs. That's the most efficient way to do it. So what you get is a T-shaped molecule. It'll look like this. So it's T-shaped. You have bromine in the middle, fluorine up, fluorine down, one in the plane of the board, and then you got a lone pair coming out at you, and a lone pair going behind the plane. And that minimizes the number of negative interactions. So these bond angles would be 90 were it not for the fact that these 2 lone pairs are here. They're going to slightly bend that for. So I predict bond angle here would be slightly less than 90 degrees. If you look it up, you can let me know. I didn't look it up, but I predict it would be around 89, 88 degrees. Okay, C, that's done now. Perchlorate is D. So we have chlorine, you have oxygen. Chlorine has 7 valence electrons. Oxygen, being a chalcogen, has 6, and there are 4 oxygen atoms. And there's an extra charge for the presence of a -1. So 4 times 6, 24 plus 8 gives you 32 electrons to account for 8 people. Where's the rest of the class? I know officially you don't have to be here till April 6th, but it's your education. Okay, so you have your chlorine as your central atom, put your oxygens in there, and then disperse your extra electrons as the valence shell for the oxygen atoms. And what do we use up here? 4 times 6 is 24. 26, 28, 30, 32. That uses up all the electrons. But if you draw it this way, you're going to have a negative charge on each one of the oxygen atoms, and chlorine is going to have a +3 charge because it only has full possession of 4 electrons. The way to remedy that is to share lone pairs between oxygen and chlorine, creating some double bond character, and this is what perchlorate ends up looking like. Everything has an octet. Chlorine clearly has an expanded octet, and all the formal charges disappear except for that one on the oxygen atom. So that way you end up with only one oxygen with an actual formal charge. What's really happening is you get delocalization of that charge. So you get 7 bonds shared over 4 positions. So it's 7/4 bond character. And the bond lengths will reflect it when they measure them experimentally. When you have 4 domains, you're going to get, and they're all bonding, 4 bonding, so that's going to be tetrahedral. So I hate drawing these ones because they're double bonds make it more cumbersome. Anyway, it looks like this. Draw 2 in the plane of the board, 1 coming out at you, that's one of the, let's make it the one with the charge on it. And then 1 going behind the plane of the blackboard. All right, and those bond angles are going to be 109.5 degrees. And obviously it's a polar molecule because it has a formal charge, so it does, and perchlorate is quite soluble in water. Xenon Difluoride is E. You got xenon, you got fluorine. Xenon, you don't think xenon can form compounds. You know, you've always been taught that noble gases are not are inert, but there are conditions that you can subject them to in which they will form compounds, and it usually involves fluorine as the other atom, because fluorine is quite reactive. So there's 8 valence electrons on xenon, 7 on fluorine, and there's 2 of them in the compound, so 14 plus 8 gives you 22 electrons to account for in the diagram. So start by connecting fluorine atoms to the xenon, dispersing the extra electrons. That uses up 12, 14, 16, 18, 20, 22. So there's 3 lone pairs on the central atom. If you draw that, first of all, you got 5 domains. 1, 2, 3, 4, 5. 5 domains points to trigonal bipyramidal, but when you have 3 lone pairs, it actually comes out looking linear. The lone pairs end up equatorial. That's the best way they can stay apart from each other. They stay at a 120-degree angle to each other if they can remain equatorial. So let me just write all this down. 5 domains, 3 lone pairs, 2 bonding pairs. So what you're going to get is actually called linear, and the xenon will go like in the middle, fluorine 1 up, 1 down, and you could have 1 lone pair going sideways in the plane of the board, 1 coming out at you, and then 1 going behind the plane of the board. So xenon difluoride is a linear molecule, but with a skirt of lone pairs. And it's also nonpolar, incidentally, because the dipole will go towards fluorine in this case, and towards fluorine in that case. Those 2 dipoles are directly opposite each other, so they cancel out. The molecule should be nonpolar. It should be soluble in nonpolar solvents. As they say, like dissolves like. Now let's look at the bromite anion, sorry. 20 electrons have to be accounted for in bromite. This is what you're going to get. That uses up 12, 14, 16, 18, 20. If you draw it this way, the oxygens each have a -1 charge. Bromine will have a plus charge because it actually only has possession of 2, 4, 5, 6 electrons, although it has a full octet. And one way you can remedy all these extra formal charges is to redraw it like this, so it'll have some double bond character. It'll still have a minus charge on that oxygen atom. And there will be a double bond over here. Really what you got is 3 bonds shared over 2 positions. Okay, now when you have 4 domains, 1, 2, 3, 4, two of which are lone pairs and 2 are bonding, that's pointing to a tetrahedral archetype. But when a tetrahedral archetype has 2 lone pairs, we call it bent. So the molecule is going to look like this. So let's consider these in the plane of the board. And there's one lone pair coming out at you, and another lone pair going behind the plane. All right, so it's a tetrahedral archetype, but it's like water, essentially. Water is a tetrahedral archetype, but because of the lone pairs, we only see the oxygen atoms and they're bent because of the presence of those lone pairs. All right. I'm tempted to stop here and just give you some homework to practice so you can be ready for when we really kick off the next chapter, which is to go to kinetics. Not that there's any connection, but you know, I'm thinking of doing this. I'm going to write the notes up. I might have to rewrite the notes because I didn't bring my whole binder with me to Alberta. I didn't think I was going to be stuck here. So I might end up rewriting some of the notes for kinetics and just showing you the appropriate pages so you can copy them down. I can't think of any other way to do this. If you can think of a better system, let me know. And you know what? This is a short class. Let's add a few more exercises. I'm going to do 922 with you, and then we'll call it quits. Okay? 922 has 1, 2, 3, 4, 5, 6 more problems that I can show you. Practice makes perfect. Maybe you know what I'll do? Just to put off having to write a ton of notes, maybe what I'll do is I'll cover the chapter on equilibria before I do kinetics. I'll leave kinetics for later on in the year, because that way there's a good chance I'll be back in Toronto by then, and I'll be able to just show you the notes I have there already, because to avoid duplication of work. Because I'm just, if I do that chapter first, I'll give myself a ton of work. So we'll do the acid-base chapter. It's more mathematical, and more of the stuff I can do just straight on the board, and I can also direct you to the actual notes online. I have the notes already for kinetics in the playlist, thank God. So let's do 922 together. We have HCN. It says, give the electron domain and molecular geometries for the following molecules and ions. So for HCN, okay, that's kind of trivial. I'll just do that one straight up. Hydrogen cyanide, because you have a triple bond, you know that's got to be straight. So the bond angle here is 180. This is sp hybridized. Okay? There's a lone pair on this side as well. For B, it says sulfite. Let's draw out sulfite. So there's, oops, -2 charge, not 1, it's 2. So 20 electrons to account for. And if you draw sulfur with oxygens as the satellites, fill in the octets. You get 18, 20, 22, 24. Whoops, the daisy. I did something wrong here. Yeah, it's 26. 6 times 4 is 24 plus 2, 26. Nobody said anything. Not that you could have. 3 times 6 is 18, 20, 22, 24, and then 26. There you go. Okay, now that works out. Each one of these will have a -1 charge, and the sulfur will end up having a plus charge because it only has possession of 5 electrons here, so it goes 2, 3, 4, 5. So if we share one lone pair, we can reduce 2 of those formal charges down, so it'll be like that. Okay, so that gives you some double bond character, and you still have your lone pair there. So there's 4 domains here, and when you have 4 domains, it's tetrahedral. Tetrahedral, the archetype, sorry, but because of the lone pair presence, it's going to be pyramidal. So let's draw that the way it appears. Put that over here. It's pyramidal because of 4 domains, 3 bonding, and 1 lone pair. So it's going to look like this. I'm going to say, put the lone pair straight up like that, and then one oxygen as a leg, one coming out at you like this, and one going behind. Okay, so you see that it's got a pyramidal structure. Next is sulfur tetrafluoride. Sulfur tetrafluoride sulfur has 6, fluorine has 7, and there's 4 fluorine, so it's 28 plus 6, or 34 electrons to be accounted for. Fill in the octets. Four times 6 is 24, 26, 28, 30, 32. You're going to have one on the centrally located. Double check for that. 4 times 7, 28 plus 6, yeah, 34. So 34 electrons are accounted for. When you have 5 domains with 1 lone pair and 4 bonding pairs, what you get is a sawhorse. Or sometimes they'll call it seesaw. I forget what they said in the book. It's one of those two. I've seen both. So a sawhorse is like a seesaw, right? It's got the plank and then the 2 legs. So you can draw it this way. Draw the sulfur atom there. And 1 fluorine up, 1 fluorine down. That's the plank, as it were, for the seesaw. And here's the legs. One's coming out at you. One's going up behind. No, sorry, fluorine atoms. And then the kid standing in the middle of the seesaw is that lone pair. Okay, and that's your sawhorse. And this bond angle is probably going to be a little bit less than a little bit more than 180. So meaning. The bond angle here is going to be slightly less than 90. Okay, so if you could imagine this molecule turned like that, and the fluorine atom would be like this, and then the seesaw, the kid would be standing in the middle of the seesaw right at the pivot point, and that's how you can picture that. The next one is PF6 with a negative charge. Still with me? 5 people. So 42 plus 6 is 48 electrons to take into account. Okay, 6 times 6 is 36, plus 12 gives you 48. You use up all the electrons. Phosphorus likes to have possession of 5 electrons, but it has, in this case, it's got 6, so the negative charge is actually sitting on the phosphorus atom, which seems a little bit odd, but remember there's 6 fluorine atoms arrayed around it, and fluorine is a lot more electronegative than phosphorus, so they're probably going to pull those electrons towards themselves, so the phosphorus probably doesn't really feel that negative charge. It's being dispersed by the presence of all those fluorine atoms. You have 6 domains, all bonding, so that points to an octahedral geometry. And the way you would draw it, I'll draw it over here. 1 up, 1 down, 2 coming at you, and 2 going behind the plane of the board. Bond angles were all 90, and there's a negative charge on the phosphorus atom. This is going to be, well, it would have been non-polar, but it's got a formal charge of -1, so it's probably a very soft -1 charge. PF6 is probably an interesting anion. It would probably be ideal for coupling to something that has a very soft and diffuse plus charge, some inorganic cation. It would be the perfect counterion for a large inorganic cation. The next one we have is ammonium chloride. Ammonium chloride, it's just like ammonium, essentially, where one of the hydrogens is replaced by chlorine. Five electrons are on nitrogen, 1 on each hydrogen, of which there are 3, and chlorine has 7. And then because there's a plus charge, you got to subtract 1, so at the end you end up with 8 plus 7, 15, minus 1, 14 electrons. You'll notice that in all stable Lewis structures, you're going to have an even number of electrons. If you don't have an even number of electrons, you've got a radical, and radicals are not stable. They can exist, but they're not comfortable. They're molecules that have to react with something else very quickly to restabilize. So it'll look like this. Two, 4, 6, 8 plus 4, no, plus 6 gives you 14. So that uses up all the electrons. The nitrogen is going to have a plus charge because it actually wants to have full possession of 5 electrons, but it only has possession of 4 in this case. And because you have 4 domains, all bonding, that's a tetrahedral molecule. So if you want to draw it properly, you'd say, two hydrogens in the plane of the board, one coming out at you, and then you can make the chlorine go behind. It doesn't have to be the chlorine going behind. I just chose it that way. You could put any one of them and replace them. It's pretty well symmetrical. And you get 109.5 degree bond angle. And the last one we're going to do is azide. 3 nitrogen atoms with a -1 charge. Okay. Of course, you could probably, if you go on the Vesper theory playlist, you'll probably see all this worked out on a big board with notes. So feel free to indulge. There's 5 nitrogen atoms, 15 electrons you have to account for. Oh, forgot the negative charge. There's an extra electron. So that's 16 electrons to account for. Draw all of them in a line. That's what I think is going to work. And azide's a funny chemical because it's not very stable. It's both an explosive and a poison. That's pretty rare to find. So let's use up as many electrons as we can, giving them octets. 2, 4, 6, 8, 10, 12, 14. Okay, let's give this guy an octet and see what we get. That's 16. So 2, 4, 6, 8, 10, 12, 14, 16. Okay, the only thing that has an octet is this one, but nitrogen does not feel comfortable with that. That's not going to work. That's too many charges. Let's put it over here. See how well that works. So in this case, this nitrogen has possession of 5 electrons. This nitrogen has possession of 5 electrons. This nitrogen has possession of 6 electrons, and it's got a negative charge. So the negative charge on azide is taken care of. And there's probably some resonance structures that we could draw that would help redistribute that negative charge. I suppose you could turn this into a double bond, and then you would get this. Let's see what that looks like. 2, 4, 6, 8, 10, 12, 14, 16. That uses up to 16 electrons. That formal charge would be gone, but now it would be over here. And of course, it would alternate to the other side potentially. So it would, you could have this flipping over to this side. And then you would have that instead. So those are all possible Lewis structures. The central atom has 1, 2, 3 domains in both of these cases. In this case, it's got 4 domains. So I'm going to say that this is probably the major species, and it has 3 domains. Yeah, you better check on this one because I'm not 100% sure. But I'm giving you my best answer, okay? So you just check up on that one because I'm telling you, for F, I'm a little bit unsure because it's azide. And azide, it's one of these chemicals that's not particularly stable. It's when you find it hard to draw the Lewis structure, already that's telling you something. It's telling you that the molecule is probably not very stable. Anyway, look it up just to make sure, and if I'm wrong, tell me. There's 3 domains here. There's 3 domains, 1 lone pair, 2 bonding. So I'm going to say that points to a bent geometry, and it'll look something like this. And look it up after I finish this video just to make sure. And I'm going to say this bond angle is less than 120 because of that lone pair. Okay, so that's my prediction for azide. If you can prove I'm wrong and you posted it in the answers, I'll give you a bonus. And we'll see you tomorrow. Bye-bye.